quality of information that we have from exoplanets comes when they pass in front of their host star. Venus's host star is our star. And you can see it's also in multiple colors. And so as you look at different colors, the red one is first red, the yellowish one is yellow, which is the true color of images. But they have different features on the star. They also have different features on the planet, and that's a lot of what I'm going to get into. This is a 5-minute long video. I suggest you watch it dozens of times on YouTube. The first question has to be, what's an exoplanet? So an exoplanet is a planet that orbits a star outside of our solar system. And okay, what's a solar system? What's our solar system? Our solar system is composed of our sun. And sometimes in Arizona, it feels like you're on the sun. But it also has these 8 and sometimes 9, depending on which kindergarten you went to, planets. And so they're ordered. These are not to scale by any measure of size of the planet or size of the orbit, but they're in the correct order. And it's important because a lot of exoplanet scientists, we're born on Earth, where most of us, and we relate outside what we know inside. So we'll hear words like hot Jupiter. And that means that an object that's about this big or bigger is really close to its star. Or you'll hear Earth twin, which means that an object roughly the size of Earth is pretty much where Earth is. We haven't found one yet. Or you'll hear sub-Saturn, or warm Neptune, or warm Uranus, or even exo-Mercuries are now fashionable with Kepler data. And the idea is that we relate everything we know to the solar system, but the primary thing you need to remember is that exoplanets are outside the solar system. So out there, the uncharted territory is where the exoplanets are. And there are lots of them. They come in all literally shapes, well, they're all spheres, but shapes and sizes. So far, actually, well, that is not true, but that's not, I'll ask you a question later. One of them is not a sphere. So they come in different orbital configurations, geometries, distances of their planet, types of stars they orbit. It's really vastly different. And also how many planets per system. So one of the first trivia questions you get a prize for is how many exoplanets, even candidates, do we know about? How many over here? About 5,000, yes. So I go with 4,500, but it's about 5,000, you're right. That's a great answer. There's roughly 5,000 known exoplanets, and we're 20. I was in high school when the first exoplanet was detected, so 20 years, and we've known 5,000 of them. So by the time James Webb goes up and even finishes his mission, we're looking at tens or maybe hundreds of thousands of known exoplanets. In the galaxy, we predict there are 100 billion exoplanets of some size, shape, or form. So what does exoplanet look like? Technically, that would be an exoplanet. If you don't know what that is, go home and watch the movie. So, Tatooine orbits a twin star. That's not our sun. Therefore, this is what it could look like. I wish. Do we have that data? No, not yet. But we know that planets that do orbit circumbinary stars exist. And I think if you answer the first question, this is the BuzzFeed you got. I love that BuzzFeed. The first one ever detected, we affectionately called Kepler-16, we affectionately called Tatooine. And it does orbit 2 stars. Now we've got like a couple of dozen of them. So there are planets that orbit 2 stars. In fact, there's a planet that orbits in a 4-star system that's not like this. That means it orbits a twin star, and those twin stars orbit a twin star. Awesome. So we have to come back still. What does an exoplanet look like? If that was the data, I wouldn't have a job. So this is an artist rendering what an exoplanet looks like. It also has twin stars because every sci-fi artist grew up in Star Wars. And it's orbiting a planet here, like the planet over there. So it's still possible that we can find planet-sized or characteristic objects that are orbiting other planets. Like, a moon of Jupiter orbits Jupiter. We can find things like that too. Obviously, it's an artist rendering. This is kind of what we would see in the infrared. This is the kind of picturesque that we have in our minds when we talk about infrared exoplanets. It's heat coming off of the exoplanet that we can almost see. We can see some of them. Not like this. It's like an artist rendering. I'm moving further out, as you'll see soon. And do they look like this? This would be like a Earth-sized system, an Earth twin system. And finally, and this is almost close, we have images of debris disks. We can't see planets inside them. We can only infer it. 2 or 3 we can see. But these giant dust disks. Those you can see with measurements like the James Webb Space Telescope, because the dust disks emit in the infrared. We can see them in the visual as well, but we can see a lot more of them in the infrared. Finally, maybe exoplanet systems look like us. This is an artist's rendering of us if we were an exoplanet system. And my colleague here thought that this system was under attack, alien invasion. But those are comments. They're outgassing way too far outside for any LPLers, I'm sorry. But maybe it looks like us. Maybe it's, it's some star with 4 inner planets, an asteroid belt, 4 outer planets, another big asteroid-ish belt, comet belt. And really bad news. That's what an exoplanet system looks like to us. It's just a bunch of dots next to a star. And in fact, this star has been blocked out by a thing called a coronagraph. And James Webb has a coronagraph, so we could reproduce images like this. Now here is 4 different planets, B, C, D, and E, that are orbiting a star called HR 8799. This image was taken in LBT, which is right here in Arizona, like an hour south of here. One of the most advanced telescopes in the world. 2 twin 6 or 8 meter telescopes, 8 I think. 2 twin 8 meter dishes side by side, beautiful, able to grab amazing observations of exoplanets in many different forms. And here's an even more interesting and updated measurement of that same exact star system, where you have different bands. And this here, the 3.3 microns, that's the kind of thing that we're going to be able to see with James Webb. This again was all done with LBT, but an hour south. And this is here, this is closer to the human eye visibility. So the second question I have, how many directly imaged multi-planet systems do we know about? Over here? 4. Probably that's not correct. We know 4 planets in that system. Do we have another one? Any other questions? Any answers? How many do we know about? In the back? 10,000. Well, we only know about 4,500 exoplanets total. Soon. I hope. In the backpack? 4 was closest. Want to get to it? Okay, one more try. Okay, 4 was closest. So give it to 4. Sorry. 1 is the answer. Closest for and then over. I apologize. 1 is the answer back there. I'm hoping it's a piece of shirt because I knew first. We know about exactly 1 multi-planet system. We have 15 to 20 directly imaged planetary systems, but only 1 of them has more than a single planet in there. And that's important because Kepler, which is this awesome space telescope that looked for exoplanets, we found roughly 4,000 of them. The biggest prolific exoplanet finder found almost all planetary systems come in multiples. So if we're only finding 1 directly imaged planet where we can see individual planets around the star, why do we not find them directly if we find them doing different methods I'll talk about in a second? The reason I bring that up, not that we know it, we don't know why. But the reason I bring it up is that James Webb can help solve this problem. One of the best opportunities for James Webb exoplanets is to look for systems like this by targeting other known systems that have exoplanets and look for ones that we can see farther away from their star. So James Webb is a great opportunity to branch that out and branch between what's called transiting exoplanets and directly imaged exoplanets. So I personally work on transiting exoplanets. To get to the sciencey stuff, basically, when the planet passes in front of the star, just like the Venus transit you saw earlier, exactly like that verbatim. When it passes in front of the star, you can see a portion of the star blocked out. If you stare at the star long enough, you can watch the light dim slightly. That dimming changes with your wavelength. So this blue region here on the outside there, that's the observable atmosphere. And being able to detect the observable atmosphere means you can detect the molecules inside of it. Water, methane, ammonia, CO2, CO, and you can tell what it's made of, and you can tell how it was formed, you can tell maybe how we were formed. That's the whole point. Now, this is a great graphic. I have really bad news. Pops up. Okay, can you see flickering? This is what a star looks like in an infrared telescope named Spitzer. If you can look closely, you can see some of the boxes are changing in their fluctuations. We look for that fluctuation in light coming from the star, and you can measure the planet itself. I think it's going to move to the next slide. So this mission Spitzer cost another $500 million, one of the most impressive telescopes we've ever had, and we get 8 pixels. With James Webb, we get about 9 pixels. But they're really symmetrical. That's important. They're stable. They're clean. I promise you this will work. Because, so here's what normal people think an exoplanet atmosphere looks like. Don't worry, you're normal. Here's what I think an exoplanet atmosphere looks like. When you measure the spectrum of an exoplanet, you're looking for ups and downs, peaks and troughs, like a sine wave. So if you can see that there's more absorption in the middle and less absorption on the edges, that's the planet looks bigger at 1.4 microns and smaller, really tiny bit smaller at the wings there. You know you detected the atmosphere, which is that blue annulus you saw before. So this is what water detection looks like around an exo-Neptune, the only one so far of its kind. And that's water. But if we branch out, and I made these simulations myself, if we branch out, we can see this is what water looks like at much longer wavelengths. Sciencey stuff. So these bumps and wiggles, exactly what I had before, more absorption means the planet looks bigger, smaller. All you have to know is that there's peaks and troughs. There's ups and downs, and if you can get the exact sequence of those ups and downs, you can tell what molecule it is. And that's really important because that's all HST can do. HST can only measure this peak here and then left of it, which is off the chart because we don't care about it anymore. But James Webb can literally measure every peak and trough in that spectrum. And it does it using 4 amazing, beautiful instruments. We can do it using different calibrated sources, different kinds of technology. And granted, we can know if a planet has water because of HST, but not all of them. And so the sensitivity of James Webb allows us to get better water measurements. It's way more important than that. Water is important for life, but so is carbon. And so we're carbon-based life forms. And so you want to know methane, which is carbon and 4 hydrogens. We want to be able to detect that as well. Okay, so HST can only observe this. Those are not really observable with HST. They do exist theoretically, but these we can measure with James Webb. So why James Webb for exoplanets? Because you can see things in the atmosphere you cannot see with any technology we have today. Literally, no technology right now can see these giant bumps, huge features, because they just don't have the right spectroscopic range or they don't have the right sensitivity. Last 2 slides, carbon monoxide, CO, feel like the fire gets off. Also a very rich carbon-bearing molecule, so it can be a source of carbon for the formation of life. These 2 bands can only be seen with James Webb, and nothing can be seen with HST. Last one of these. Carbon dioxide, a greenhouse gas, terrible, but otherwise natural at some point. These peaks here can only be seen with James Webb, and nothing can be seen with HST. So we need the James Webb Space Telescope to find out where is the carbon, and at many levels, where is the other oxygen? If the water carries 1 oxygen, carbon monoxide carries 1 oxygen, carbon dioxide carries 2 oxygens. So we want to be able to find out where's the carbon, where's the oxygen, and where's the water. And so that's what we need the James Webb Space Telescope for. Small bit of history, and this is the last slide I have. When the James Webb was first pioneerly conceived was in 1996. It was called the Next Generation Space Telescope. At that time, we discovered the first exoplanet, 51 Peg. When it was named James Webb and finally put into its current stage, 99% of its current stage, was when we found the first atmosphere, meaning spectroscopic measurement of an exoplanet. Currently, we know about roughly 5,000. I like to put middle of the road, let's say 4,500 exoplanets, but we have less than 100 spectrum. Meaning we have less than 100 atmospheres, we have less than 100 understanding of the composition of the planet. And with the James Webb, within the first 5 years of its possibly 15-year mission, we can expect 3, and on an upper limit, 500 different spectra. We can start to understand what's out there, where is the molecules, and that all comes back to where did we come from. We're not going to find life itself, we can find out the kind of molecules that life forms from. And that's my last pitch. So, in finality's favor, there's also the 2 slides that we orchestrated as giving pulses to the planets, which is totally relevant. I don't know that. There it is, October 23rd, 23rd. Thank you very much. Questions? Yes?
You mentioned 51 Pegasi in your last slide. Now,
Yep.
my understanding is that that's an unusual one because it's an exoplanet around a neutron star.
I don't think it is.
No?
No, PSR, blah, 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 is a neutron star. That was discovered in 1992. So the 51 Peg, I don't know what kind of star orbit, but it's a normal class star, and it's a Jupiter-sized planet.
In that case,
Okay.
is there, that's like basically a question. Is there any research planned for pulsar planets with the
There's, I believe, only been one pulsar planet detected, so not really. You can't do anything with the ones we know because translating them is not easy since the neutron star is incredibly tiny. So translating it doesn't really work, and translating we get all of the information from. In the back? Not with the James Webb Space Telescope, we cannot detect oxygen. There is this tiny possibility that with the 10 years from now technology, which is being built and funded right now, that you can detect oxygen on a few planets. But it's incredibly difficult, more difficult than anything we've ever tried before, mostly because our atmosphere has oxygen, and a space telescope to detect it is even more pricey, so it's difficult. That's the end. Yeah. Any more questions? No? Okay.
If not, next time we'll pass fingers again. So, before you head out, this one slide that Jonathan set up here, in the group of Tucson Symphony Orchestra, it's doing Gustav Holm's Planet Suite. Some of you have heard this thing, it's very awesome. If you've heard the Star Wars Day of March, it's like go days of Mars and God of War. And we coordinate spacecraft with us, so we'll meet there, doing the shows, and also for next that month, we'll be talking about the Planet Suite, the stories behind the planets, and then we'll have mission specialists here who have run missions to each of those planets. We'll probably focus on the big ones, and it should be a lot of fun. So make sure you don't miss that. There are discovery tickets if you like should see the planets show that are available. The promo code for that is called Spacecraft, and if you scan that QR code, you can find this poster up on our webpage. Then I'll link you to the Game Master site so that you can buy them. Before you head out, I have to apologize for the pizza not making the appearance. I don't know what happened. We'll fix that by next month. And again, stay down, have some beer, talk with our speakers. Stacey even bought a lovely little model of Space Telescope. Don't touch it, it's really fragile, and she will get really angry with you for breaking. But it is very cool to come look at, so please have a look. And thank you all for coming out again.